Hello, again, my name is Ajeng, and as Professor Payne said, I'll be talking a little bit about some excavations that I did with a retired professor from Palomar College in Togo, Africa, along with the research that followed about a year later with the Field Museum. So a little bit about me. I am a current Palomar student. I was first enrolled in 2016 as an art historian, and I transferred to UCSD in 2019, where I got my BA. But when I graduated, I realized there's not really anything I can do with an art history degree, aside become a professor, which is not really what I would like to do. So I was looking into some graduate programs because I was like, well, that's kind of the next step for me. And I discovered some conservation programs, which I am incredibly interested in. And particularly, I would like to do archaeological conservation. So I came back to Palomar and I started enrolling in a lot of archaeological courses. And when I was taking the intro to archaeological excavation, the retired professor, Phil DeBarros, came and offered for any students who'd be interested to come along with him to do excavations in Togo, Africa. And that is where we will be starting. So we went in December of 2021 into January of 2022. We were excavating units at a site he had previously excavated in, sorry, my bad. So we were on units that he had dug in about 20 years ago. It was a burial ground for what they believe is a family. The idea that they have for this site is as members of the family die, they just re-expose the burials and just kind of add people as time goes on. And so what we had mainly been focusing on during the actual excavations was to look at their mortuary patterns. Our whole goal was to just expose the burials, and we were going to have a couple of Frenchmen come in and they would do the research into what kind of patterns were going on in these ancient burials. And the unit that I was in charge of, which is right here, Unit 54, is where these particular beads came out of. While I was personally there, we only found maybe 2 or 3, and about a week after I left is when they found the bulk of them. There were several hundred that came out of this excavation. So this is a clump of dirt that had a lot of the beads, so you can see them here and here as well. So about a year later, probably must have been March earlier this year, Professor DeBarros reached out to Professor Payne and asked if there would be any students interested in doing any research on these particular beads. And I jumped at the opportunity because the research would be at the Field Museum, and I'm incredibly interested in doing museum work. So the beads were going to be analyzed using LA-ICP-MS, which is laser ablation inductively coupled mass spectroscopy. So I was in charge of transporting the beads to Chicago, and I would work with the person who does LA-ICP-MS. Her name is Laure. I do not know how to pronounce her last name. I apologize. And so LA-ICP-MS is a technique that allows scientists to analyze the elemental composition of solid samples. The particular machine we used is actually more so for solvents, so liquid samples. So it's a little bit tricky trying to do tests on solid material. But the two sort of goals that we had with this analysis was to first look at the chemical composition of these beads, considering that they were carnelian. We knew going in they were going to be mostly silica, because that's just what they're made of. And then our second sort of goal was to look at the sourcing. Are they coming from the same source? And if they are, can we figure out what source that is? So this is a little video of me loading up the beads into the machine. So we would do 3 to 4 batches a day with 5 beads in each batch. We would also compare 5 standard or control samples to calibrate the machine and for our conversions later when we were doing the actual analysis. And so they're currently being placed into the chamber tray, and you can see me kind of adjusting the height of the tray because you have to get it as high as possible to get it as close to the laser as possible, but also not so high that you can't put the tray back into the machine. And so the photo right here is the material in there, and then the laser is actually working. So this picture right here is how they were all set up. We just used like poster putty because it's really easy to work with, and it allows for really, really easy adjustment of heights. And then this little video is when you put the beads in the machine, you have to manually plot in every single point that the laser is going to hit. So you have to zoom in to, I believe it's like 100 microns. You have to get really, really close to the surface of the beads, and then go in and do 10 dots per bead, and it just gives you an average sample by the end of it. And so it takes a very, very long time, and it's kind of tedious, but it was really, really interesting. And so what I was doing there was just making sure that the samples that were coming in, the numbers were adding up to what we were expecting, because if they were coming in at very, very low or very, very high, we knew something was wrong, so we would have to cancel the tests for that particular batch. So again, this is the laser ablation machine. Laser ablation is a high-energy laser beam that you focus on the surface of your sample, and it creates a tiny little crater by vaporizing a small amount of that material, which gets sucked up and then moved to the mass spec machine. And then I do have a little photo or video, and so you can actually see the laser working, if the video works. Yeah, so that's the actual laser, and then it leaves those little craters, and there's a little cup around the laser that sucks up any of the machine that comes through it. And so this is the MS, the mass spec machine. There's this little tube that has a bit of, I believe it's argon gas, that carries the material over. And so the mass spec has, essentially it vaporizes the material, so that way they can bump it up into a really, really high temperature. There's, you can see this little green spot, and that's the plasma. And once it's in the plasma, the atoms and the ions become like supercharged, they become ionized, and by using those ions, we're able to do the mass spec, which, let's see, the ionized particles are introduced into the mass spec machine, which will then separate the ions based on their mass to charge ratio, so essentially how heavy it is in addition to any extra electrons that are there. And using those weights, we can identify which different elements are present in those samples. So this is a very standard result of what we got of one of our beads. So as I said, most of it is going to be silica with very, very trace amounts of other material. In this case, there would be like iron inclusions. However, we did have a number of different materials in the beads just for how they develop in geology. And so you'll get a sample like this, where the laser accidentally hits an inclusion. So when you're expecting to have something like over 99% of silica, but then it's almost 75% of iron. So within all of our beads, we only had one sample that was heavily skewed due to this. Pretty much everything else fell within our range. So across 113 beads, that's pretty good. But so far, we've done a little bit of analysis. We haven't done too much in regards to finding out where the sourcing is, but the idea is they're most likely all coming from the same source. But any further research that's going to be done is still in the works. So we'll see what happens next. But that is my presentation, so if you have any questions.